Okay, thank you very much. And thank you for the opportunity. So I'm going to present you the work we have been doing on the biological control of the fall armyworm in Africa. So I'm sorry, maybe you guys are hearing a noise behind me, and there's an helicopter that is passing by. So then they work on the biological control of the fall armyworm starting when, of course, the insects was invaded Africa. And some of the scientists in the region, we thought that we should work on biological control and trying to find if there are natural enemies that have been recruited by the new pests. And in fact, in Africa, there was a related species such as Spodoptera littoralis, Spodoptera exampta, and Spodoptera exigua. And we thought that those related species might share the natural enemies of the fall armyworm. And this was based on something that has already been observed elsewhere, and it is called new associations. So then this work has also been facilitated by the fact that there was a large group of scientists in Africa that were already working on biological control of different pests. So then it was quite easy for them to do that. Sorry. So then what are the steps to be taken when you want to implement biological control? So first you have to look at the existing natural enemies. And when you identify the natural enemies, you need to develop mass culture of those natural enemies, because if you don't have the insects in culture, you cannot do any work. And then you, of course, you follow it with the effectiveness studies in the laboratory. And from the insects that you identified as effective in the laboratory, you validate them in the field, and you develop the release techniques. So then for egg parasitoid, there are two ways of getting the natural enemies of eggs. So you can rely on the eggs that have been laid by the fall armyworm in the field, and then you collect the egg masses and you take them back to your laboratory and you incubate them and you wait for them to emerge, and you will see whatever has emerged as a parasitoid, and then you try to identify them. Another option is to, from your laboratory, if you have your fall armyworm culture, so you collect the egg masses from your laboratory and you expose your egg in the field, and this is called the sentinel eggs technique. And you make sure that you put a kind of mesh on the eggs to avoid the eggs to be eaten by predators, because you want your eggs to be parasitized. So the same way, after a few days, you take back your egg masses to the lab and you incubate and you wait for the emergence. For larvae parasitoid, it's the same way. You collect the larvae in the field, but you have to make sure that you collect all stages, not only big larvae. So you have to collect small ones, medium size, and large, to make sure that you have all the type of parasitoid that could parasitize the different larvae. And you can also here use a sentinel larval technique if you don't have enough a high population in the field. You can also collect your larvae from your lab and take them back to the field. You place them on the crop and you wait for them to be parasitized. You incubate and you wait for the emergence. And when you get your emergence, you get your parasitoids identified. So what we have been able to do so far in Africa, we have been able to collect a lot of parasitoids, egg parasitoids from the family Platygastridae and from the Trichogrammatidae families. So we have different species. And we do have also many Braconidae larvae parasitoids. We have Ichthyomonidae larvae parasitoids. We also have Tachinidae parasitoids. So you can see that the parasitoids have been collected in many places in Africa, in Central Africa, West Africa, and Southern Africa. So there is a large diversity of natural enemies that are there that can be used for biological control of the falling armyworm. And I believe the same is also there in the Philippines. So then here are pictures of some of the parasitoids that we have collected in different places. And among them, this Telenomus, which is one of the egg parasites, it has been used worldwide. I mean, let's say the area of origin of the fall armyworm in the Americas has been largely used there for biological control of the fall armyworm. You also have different species that I'm showing here with the pictures. So how to use the natural enemies? So since they are there, you have to conserve them. This is the first step. And from the preview presentation, you have seen many agroecological approaches, which are very good and very effective, and they help to maintain the natural enemies in the field. So then it's mainly based on habitat management techniques, push-pull, agroforestry, for your natural enemies to be there and to do the good work. But if you come and you spray randomly very toxic pesticides, so you will kill your natural enemies and you won't get the benefit you could expect from them. So then, first of all, get your natural enemies to do the work for you by having good farming practices. And this applies mainly to the natural enemies that are very difficult to mass culture. Let's say the predators and some of the larvae parasites are very difficult to mass culture and to be released in the field. So then you get them to do the good work for you in the field first. And you have this picture on the right that I borrowed from Harrison and Hall, which clearly explains how those natural enemies can be used in the field. For parasitoids that can be easily mass culture, like the egg parasitoids, so then you can develop your mass culture. For instance, Trichogramma species, you can mass culture them on many caterpillars that develop on storage commodities, like the rice moth, Corsara cephalonica, or the meal moth, Ephesia quieniela. Those are worldwide being used for mass culture of Trichogramma. For Telenomus, it is mainly mass culture on the fall armyworm itself. So then you have to get your mass culture of fall armyworm in your lab, and then mass culture Telenomus on it. So you can see here some of the data that you have been collected on Telenomus and one of the Trichogramma species that we had in our area here. You have the development stage, the time of development from eggs to adults, that is about 11 days for Telenomus and 9 days for Trichogramma. You also have the sex ratio and also the adult lifespan. For Telenomus, it's above 17 days, and for Telenomus, it's about 11.3 days. So those are information that are critical. When you want to do biological control, you need to know the insects you are dealing with. So then you need to do the basic studies in your laboratory to use them in the field later on. And we have been also doing some comparison of the effectiveness of Telenomus and Trichogramma. So you can see here that the Trichogramma species that we have in my place was less effective than Telenomus for parasitizing the eggs that are fully covered by you. If you are familiar with egg masses of fall armyworm, you may remember that some of the egg masses are fully covered with a scale here, compared to some are not fully covered. So then Trichogramma is able to parasitize the eggs that are not covered, while Telenomus can parasitize both. So then Telenomus is more effective in terms of parasitizing egg masses of the fall armyworm as compared to Trichogramma, the species that I have been dealing with. So here you can also see the assessment that we did in the laboratory. So, and you have the number of progeny that emerged from the parasite eggs. And as I said, again, Telenomus give more parasites when, regardless of the type of egg mass cell that's given to him. And we also did a study to understand if there is any preference of for the parasite depending on the egg's age. in no choice situation and choice situation. So you can see that Telenomus remis prefer parasitizing the 1 day old egg masses as compared to 2 and 3 days in no choice condition. And in a choice condition, it will also parasitize mostly the 1 day egg masses, 1 day old. So we have also developed a releasing technique. So we have been using the egg cards technique. So we parasitize the eggs in the lab on a card, and we put the card in the envelope, and then we cover the card with a fine mesh to prevent predation of the parasitized eggs, and then we put them in the field, and the next day they will start emerging. So depending on the cross, the species, your environment, for Telenomus remis, what is recommended goes from 20,000 individual parasitoids to 200,000 parasitoids per hectare. So this is something that you need to study in your context, in your area, to identify the number of parasitoids that are needed to protect 1 hectare. So in our case, we release about 15 Telenomus remis female for 100 egg masses, and we release them once in the season. So, but the number of releases will depend also in the number of generation of fall armyworm you get in your field. So this is something that needs to be contextualized. So you can see here the releases that we did in the field, and when we release Telenomus remis, we're about to get above 60% egg parasites, not the egg masses, the individual eggs within the egg masses. Above 60% of the eggs were parasitized in the fields where the parasites were released, as compared to the control where you get less than 10% egg parasitism, which is actually the natural egg parasitism. Parasitoids were not released there. So, and you can see that when you release the parasitoid, you get a good emergence of progeny, which means that the first parasitoid, the first batch of parasitoid that you release, they will multiply in the fields and go and parasite egg masses, new freshly laid egg masses. So I am sharing here figures from different countries. In Ghana, for instance, there was contrasting results when we released Telenomus remis. As I said, you need to study your parasitoid in your context and see how and when they have to be released to get the effectiveness that you expected. So for instance, in Kenya, the releases of Telenomus remis, Trichogramma chylonis, and also a larvae parasitoid Cortesia ICP gave very encouraging results with a parasitism of between 55% and 38%, depending on the species. There is also another good candidate, Trichogramma mwanzai, which gave about 70% parasitism of the fall armyworms in Tanzania. So you may remember that I was telling that the Trichogramma species that I use in my place was not effective, but there are other Trichogramma species that are quite effective. For instance, Trichogramma mwanzai and other Trichogramma species. Then you have to test the Trichogramma species that you have in your area and see how effective they are as compared to Telenomus. Because I believe Telenomus is also available in the Philippines, because the center of origin of Telenomus is the Malaysia Peninsula, and it's available in India in many places. So that I believe it's also there in the Philippines. And what about the economics of release of Telenomus and Trichogramma? So as I said at the beginning, Trichogramma is one of the most used parasitoids in biological control worldwide for different insect species, including the fall armyworm. They are cost effective, and especially when they are reared on storage pests. Telenomus has been mainly used in Venezuela and other countries in the America. It is also an effective, economical effective parasitoid. But the challenge so far has been the mass rearing, to get the cost-effective mass rearing techniques. Because, as I said, in my case, I mass culture them on fall armyworm, and it's not in all places that you can mass culture fall armyworm itself at a cost-effective manner. So there was another parasite that we have been trying. This is also a worldwide known parasite, larvae parasite that develop on many species of pests, and in our places it's mainly on the millet head miner. So it's also occurred on the carrot mouth, on pomegranate, on tomato, on the Helicobacter armigera, on the tea looper, so many species. And colonies of Armyworm can be easily developed on the rice mouth in the laboratory. And we noticed that this parasite can complete development on the larvae of the fall armyworm, the caterpillars of the fall armyworm. However, they don't produce enough progenies. So there was a study in India where they said that it's also an effective parasite against the fall armyworm. In our case, we noticed that the parasite was able to sting and inject venom in the larvae and then kill them, especially the 3 to 6 stages. It's also able to parasite the stage 5 and 6. It could be used in augmentative release to work as an insecticide because you don't get enough progeny. So if you do the mass releases, you will get control because we are going at least by the host feeding behavior. They will kill your parasite. If they will kill your fall armyworm. So this is also another parasite to be considered if it's available in your place. So when you have you want to develop biological control, of course, you need to develop national programs and private sector capacities, because parasites, they have to be multiplied somewhere, maybe to be produced and supplied to farmers. I don't know the context of the Philippines. Is there any willingness of farmers to buy biocontrol agents? But this is a model that can be used because this is a model that we have been using in my place. Developing private companies or farmers, cooperatives to produce natural enemies and sell it to the fellow farmers. This is something that is working in my place. So, but it has to be considered also in your place depending on your context. And yes, before finishing, I would just like to say that we have facilities for capacity building on biological control of the fall armyworm, especially the mass culture of the parasite. So we are there, and if you guys are interested, we provided some trainings for people from the Nepal, let's say Cambodia, Vietnam, and Bangladesh back in 2019. So we are available to provide such training to anyone that is needed. So we also develop a manual on how to mass culture the